Hello, this is Jack Jackson, and we're back working on a series of videos where we're talking about L'Hopital's rule. And we've looked at several different indeterminate forms where we could use L'Hopital's rule or perhaps manipulate it, an expression into the form where we can use L'Hopital's rule. And remember, L'Hopital's rule can only actually be applied if the thing that you're taking the limit of has the form 0 over 0 or plus or minus infinity over infinity. In this video, we're going to talk about an indeterminate form where you get infinity minus infinity and see what we could do with that to manipulate it so that it's a form that we can use L'Hopital's rule. And the basic idea is you just have to combine what you have into a single fraction where it has the form 0 over 0 or infinity over infinity. And what that typically means is, getting a common denominator and adding those together. So using our fraction arithmetic and algebra skills there. Okay, so let's look at an example here. See if you can do this one on your own. So let me just kind of give you the outline and see if you can try it yourself. So here you have the limit as x approaches 1 of x over x minus 1 minus 1 over natural log of x. And if you do the one-sided limits, you either get infinity or minus infinity for each of these two fractions. So this has basically the form infinity minus infinity. So what you want to do is get a common denominator, add them together, then you'll have a single fraction, and you should have the form either 0 over 0 or infinity over infinity. Then you can apply L'Hopital's rule, and it's similar to some of the problems we've done in the past. Okay, so see if you can do that on your own, and then come back and check your work with the rest of the video. Press pause now. Okay, so let's see if we can do that. First of all, let's verify again that this is the formula, the form that we talked about. So notice that it's undefined at 1. If you put in a 1 here, you're dividing by 0 on the first fraction, so that alone makes it undefined. Natural logarithm of 1 is defined. It's 0, but 1 over 0, again, is undefined. So we're basically dividing by 0 in both cases. And of course, when you have a constant over 0, that's going at least from one side. That's basically going to infinity or minus infinity. So actually, if you take the limit as x goes to 1 from the right, the x minus 1 is a positive number, and you basically have the form 1 over 0. So that goes to positive infinity. If you have this next one here, x over x minus 1, and you take the limit as x goes to 1 from the left, then x minus 1 is close to 0, but a little bit to the left of 0, so it's negative. And so this whole thing is going to approach, like 1 over 0, so it's going to approach negative infinity. In a similar manner here, we have 1 over log of x. As x goes to 1, log of x goes to 0, but if x is a little bit to the right of 1, the log of x is positive, so this is positive infinity, whereas if x is a little bit to the left of 1, log of x is a negative number, and so that goes to, so this one goes to negative infinity. But either way you look at it, you either get, I guess if you're coming from the right side, you get infinity minus infinity, and if you're coming from the left side, I guess actually you get negative infinity minus negative infinity. But anyway, that's the basic form there, and that we're going to use this technique on. So here, let's go through and work out the details of the proof of the limit, the derivational limit. So it basically has the form infinity minus infinity. And so what we want to do here is get a common denominator and add these together. So the common denominator is going to be x minus 1 times ln of x. So the first fraction, we're going to multiply the numerator and denominator by ln of x. The second fraction, we're going to multiply the numerator and denominator by x minus 1. Combining that together in a single fraction, the denominator is x minus 1 times ln of x. The numerator is x times ln of x. Now I'm going to distribute this minus here. So that's minus x plus 1. Okay. Now let's see what happens when we stick in a 1 here. We get a 1 here. Log of 1 is 0, so that term's 0. Negative 1 plus 1, that's also 0. 0 plus 0, that's 0 for the numerator. And this is 1 minus 1 is 0, and log of 1 is also 0, so we get 0 times 0, or 0 in the bottom. So this has a form of 0 over 0. In other words, the limit of the numerator is 0, the limit of the denominator is 0. This is exactly when we can apply L'Hopital's rule, of course, assuming everything is differentiable there, and we're building this up out of pieces of functions which are differentiable, so that's going to be differentiable. So we take the derivative of the top and the bottom separately. That's how L'Hopital's rule works. And let's do the bottom first. The derivative of the bottom, it's a product, so use the product rule. The first times derivative of the second plus the second times derivative of the first. The first factor is x minus 1. Derivative of the second, derivative of log x is 1 over x. Plus the second factor, ln of x times derivative of the first. Derivative of x minus 1 is just 1. Or 1 plus 0. 1. In the top, we've got three factors. I'm going to work right to left. The derivative of so use the sum rule. Derivative of 1 is 0. Derivative of negative x is negative 1. But for this first part here, we also use the product rule. So that's first times derivative of the second. Derivative of log x is 1 over x. Plus the second, log x, times derivative of the first. Derivative of x is 1. Now let's simplify a little bit. X times 1 over x is 1. 1 times log x is log x, negative 1. I drop the 0. And negative 1 plus 1 is 0, so the top is just ln of x. So that's the numerator. And the denominator, let's see, I'm going to distribute the 1 over x. So x times 1 over x is 1. Negative 1 times 1 over x is negative 1 over x. And of course 1 times log x is log x. So we'll just leave it like that. Now what happens if we plug in 1? That's 0 in the top. The 0 here. 1 over 1 is 1. 1 minus 1 is 0. Plus 0 is 0. So it's 0 over 0 form. Let's try L'Hopital's rule again. And so we take another derivative. Derivative of log x is 1 over x. The derivative here, the first part is 0. Okay, this is x to the negative 1. What's minus x to the negative 1? So it's negative 1 times negative 1 is positive 1. And then the x goes down to the negative 2, which can be written as 1 over x squared. Derivative of log x is 1 over x. Now at this point, we can actually just go ahead and plug in 1 everywhere because this is continuous at 1. If we plug in 1 here, here, and here, the 0 we can ignore. This is 1 over 1 is 1. 1 over 1 squared is also 1. 1 over 1 is 1 here. 1 plus 1 is 2. So you got 1 over 2 is 1/2. So we're taking the limit as x approaches 1 is 1/2. So 1 comma 1/2 is a hole in the graph. Another thing that's interesting just to look at this before we look at the graph, and we'll make some predictions of what the graph looks like. Notice that the function is undefined for negative x's because the log of a negative is undefined. It's also undefined when x is 0 because the log of 0 is undefined. What happens though, but if x is positive, it's defined, right? Logarithm is defined everywhere. Here's the function down here. The logarithm is defined everywhere that x is positive, and x over x minus 1 is defined everywhere that x is not 1. And of course, this one is undefined at x equals 1 as well because we're dividing by 0. So we know that the function is undefined at 1, but it has a limit there. What about at that end point? What happens at the end of it or at the beginning of it when x equals 0? It's undefined at x equals 0, but we know it's defined just to the right of that. What happens there? So we might want to take a limit as x approaches 0 from the right side. And actually, for this limit to make sense, it has to only be a right-sided limit. So let's see if I can go ahead and look at this. So make sure that this is actually a right-sided limit only, which of course is the only thing that makes sense for the logarithm part of it. Well, as you come in from the right side, what happens? Well, if these two limits exist separately, then we can take the two limits and see what happens. Well, this first part's continuous at 0, so we just plug in 0. 0 minus 1 is negative 1 on the bottom, 0 on the top. 0 divided by negative 1 is 0. So that first part approaches 0. Now, this part's a little more interesting. As x approaches 0, log of 0, from the right side, of course, log of 0 is undefined, but logarithm is approaching negative infinity. But if the bottom of the fraction is getting really big in absolute value, then the whole fraction, and the top is staying the same, the whole fraction approaches 0. So this whole thing approaches 0 as well, and so 0 minus 0, of course, is 0. So the limit is 0. So this tells us that 0 comma 0 is that the graph approaches that point, but that point's not a point on the graph, so it's an open dot actually boundary point on the graph because there is nothing to the left of that in the graph. So let's take a look at the graph. And I did it in Graphmatica, and you can see the hole nicely in Graphmatica. It does it correctly. Here at 1.5, 1 comma 0.5 or 1 comma 1/2. That's the hole in the graph that we expected. Now it doesn't completely show the graph very well right here near the origin. We know that actually it's continuous up until it hits the origin, and it actually doesn't actually hit the origin. It has a hole in the graph right there. Well, an open dot boundary point actually. So there should be another one of these little round circles there, and this should connect all the way up to that origin, but the origin itself is not included. So there's an open dot right there. Graphmatica didn't quite do that perfectly, but you can see what it looks like there, I think. Let's try another one. Okay? How about this one? See if you can do this one yourself now. Limit as x approaches infinity of 1 over x minus cosecant of x. First of all, verify that this is the same form we're talking about, and then see if you can use the same sort of technique. That's not what I wanted. I'm sorry. I want this to go to 0, not infinity. Let me fix that. Alright, now try it. Okay? Go ahead and press pause now. Okay, now you're back. Let's take a look at this. Notice if you plug in 0 here, 1 over 0 is basically going to infinity. And cosecant, being 1 over sine, that's also going to infinity as well. Okay, at least from one side it's going to infinity. The other side it may be going to negative infinity. Actually, if you look at these as one-sided limits, what actually happens? The limit as x goes to 0 from the right, the 1 over x goes to infinity, and the cosecant of x also goes to infinity. But if you're taking the limit as x goes to 0 from the left, they both go to minus infinity. But anyway, we have that same basic form. So let's see if we can get somewhere with this. So since these one-sided limits are kind of going in different directions, there's a potential that we could have to break this down into one-sided limits because they might be different. In fact, it turns out that you do get a full limit on this one from both sides. So let's continue with this. Okay, so I decided to rewrite cosecant of x as just 1 over sine of x. Number one, I'd just rather deal with sines and cosines if possible. So, and then I want to get a common denominator here. So I need to multiply this first fraction by sine of x over sine of x, and the second one by x over x. Now we have a common denominator, so we can just add the numerators, which is just sine x minus x. Now, what happens when we plug in 0? Sine of 0 is 0, 0x is 0, 0 times 0 is 0 in the denominator. Again, we have 0 minus 0 in the numerator, so that's 0 over 0 for the form. These functions are both, the way I've got them written now, as sines and x's. Those are continuous functions, so the numerator and denominator are both continuous functions. Not only continuous, but differentiable functions, so we can apply L'Hopital's rule. We have the right form. Of course, L'Hopital's rule says that this should be the limit of the derivative of the top divided by the derivative of the bottom. So we take those derivatives separately. The derivative of sine x is cosine x. The derivative of minus x is negative 1. So I use the sum rule there along with a couple other basic rules. In the bottom, we're going to be using the product rule. So it's the first times the derivative of the second, so it's x, times the derivative of sine x. Derivative of sine x is cosine x. Plus the second, sine x, times the derivative of the first. Derivative of x is 1. So I don't have to write that part. Now what happens when we try to plug in a 0? Cosine of 0 is 1. 1 minus 1 is 0, so that's 0 for the numerator. Cosine x is, again, 1, but 0 times 1 is 0. Sine of 0 is 0. 0 plus 0 is 0. So we get 0 over 0. Again, we can apply L'Hopital's rule. So take the derivative of the top and bottom again. Now, of course, hopefully the point is at some point we won't have this form anymore. Okay? but sometimes you have to apply L'Hopital's rule more than once. So here we take the derivative of the top and derivative of the bottom. Let's see what we have here. So the derivative of cosine x is minus sine x. Derivative of the constant here is 0. Okay? In the bottom, we have the sum rule. Derivative of the first plus the derivative of the second. Derivative of the second, derivative of sine x is cosine x. That's what we have at the end. For the first part, though, we have to use the product rule. So first is x. The derivative of the second, derivative of cosine x is minus sine x. I just put the minus out front. So it's really minus sine x times x, which is what we have here, plus the second cosine x times derivative of the first, which is derivative of x is 1. Let's see, cosine x, well, what happens if we just plug in 0 now? Sine of 0 is 0, 0 here, 0 here, 0 here, 0 here. Let's see if it works out to be something nice. Top is 0, this part is 0, cosine of 0 is 1, this is 1, this is 0 over 2 is 0. So it does work out to finally work out to a limit that time. This function actually is continuous at that point, so we can just plug in 0 and work it out. So this is the limit as x approaches 0, and notice we didn't have to worry about one side being different than the other. So this, in fact, is a hole at the origin on the graph, and here's a graph in Graphmatica, and sure enough, it graphs it correctly with a hole right there at the origin. You can see that. Okay, the next video we're going to come back and look at some other indeterminate forms that L'Hopital's rule does not apply to, but you can manipulate them in a certain way so that you can get L'Hopital's rule to apply. And these will be things of the form 1 to the infinity, 0 to the infinity, and infinity to the 0. So we'll look at those in our next video.